So we want to talk about Newton's method. Newton's method is used to find the x-intercepts, or zeros, of certain functions. Here's one example. 2x to the power of 3 plus 5x to the power of 2 minus 11x plus 4. There are other methods of finding the x-intercepts of a function like this. You can have a look at the graph here. And you see that there is one x-intercept that seems to be at minus 4, another one at plus 1/2, and another one at plus 1. And indeed, if you substitute those numbers in the equation, 2 times 1 plus 5 times 1 minus 11 plus 4 is indeed 0. So x equals 1 is a solution. And then if you know long division of polynomials, you can find the other two solutions easily. X equals 1/2 and x equals minus 4. So we don't need Newton's method for a polynomial such as this one, which has beautiful numbers as its solutions. But what happens if we take this polynomial and change it just a little bit? Look at the graph here, and we're going to just change it by a touch, which makes the solutions, however, much harder to find. So here's what we've done. Instead of the plus 4, we've changed that to a plus 3 at the end, just the very last coefficient. And that already makes it very difficult to find x-intercepts unless you use Newton's method. So here it is, Newton's method. We draw a coordinate system, and then here this is just one small part of the function, the one where it intersects the x-axis at 1/2 and plus 1. And then we identify an interval where there is a 0. So in this case, we are going to try to catch the x-intercept at x equals 1. Now let's find a point, in this case x1. And this is where we are going to start our process to find the x-intercept. And the coordinate of x1, where it intersects the function graph, is x1 for the x-coordinate and f of x1 for the y-coordinate. And then we put a tangent line on that point, and that intersects the x-axis. And that's where x2 is. And then we take f of x2 there, put a tangent line there, and then we get x3 and then x4, and those points are going to move closer and closer to the x-intercept, or the 0 of the function. So the challenge is to find the linear equation for the tangent line. I'm calling it g of x here. Well, we know the slope. The slope is f prime of x1, but we don't know the y-intercept, which I'm calling d here. So we're going to have to find it, but we do know that the point x1 and fx1, this is a point that is on the line, and we know the slope. So we know both a point on the line and the slope, and that is sufficient to find out what the y-intercept d of this linear equation is. So here I'm doing the calculations, and there we go. There's our equation, or our linear equation, or linear function, g of x. Now I'm simplifying it a bit. And then I'm setting it to 0 because x2 is the point at which g of x intersects the x-axis. And if a point is on the x-axis, that means its y-coordinate is 0. So if I set the linear equation to 0, then I should be getting a solution for x2. And here it is. x2 equals x1 minus f of x1 divided by f prime of x1. all of this just by manipulating the equation above, and that's Newton's method. Newton's method means that I pick an x1 and I subtract f of x1 divided by f prime of x1, and I get x2. And then I do the same thing with x2 and x3 and x4, and these x's go closer and closer to my x-intercept. So here's an example. This is the example we talked about earlier, where the x-intercepts were really difficult to find, as opposed to the example where the final coefficient was +4. Again, let's remember this is what the function graph looks like. I have zoomed in a bit here so that we can only see the two x-intercepts, the one at near 1/2 and the other one near 1. But you can see that they're a little bit off, so they're not exactly at 1/2 and 1 as they were in the well-behaved function earlier on. So we're going to have to work a little harder to find it. Here I have changed the scale of the y-axis so the function doesn't look quite as steep, and we can put a tangent line on it. That way we can see a bit better what happens. So this is the tangent line on our point x1, and I've chosen x equals 1.5 here to be my first point x1. And you can see the tangent line, and you can see where the tangent line intersects the x-axis, and that point is going to be much closer to the x-intercept than the x1, which is 1.5. So here we go. Let x1 be 1.5, and then f of x1, we just put the number in the equation, happens to be 4.5, and f prime of x, we need to find out what that is, so we differentiate f of x, and then again plug in x1, so we get a function value. This is 17.5. That is the slope of the tangent line at x1, and that gives us x2 according to the formula we just talked about. x2 equals x1 minus f x1 divided by f prime x1. So we've got all the numbers here, 1.5 minus 4.5 over 17.5, and we have an approximate result here for x2, which is 1.2429. When you do this on the calculator, make sure you store x2 so you don't get any rounding errors that compound after a while. Then we can figure out what f of x2 is and f prime of x2. We just use those functions that we've already found earlier and plug in the number x2. So here they are. And then we can figure out what x3 is. x3 equals x2 minus f of x2 divided by f prime of x2. We've got all of those numbers, and so the approximate result here is 1.1595. We go through this again. x4 equals x3 minus f of x3 divided by f prime of x3, and here we get 1.1496. And you can see that not much has changed here, going from x3 to x4. So this process is working pretty well here. The x's are going towards the x-intercept quite fast. And in fact, if you look at x5, it's only 1/10,000th away from x4. So if we were to calculate x6 and x7, there would be hardly any change at all. And indeed, the algebraic solution to this problem is 1.149496, and you can see that we got very, very close to it with our x5. And so there we have Newton's method.